Okay, good afternoon. Mike is anxious and eager to have you all attend the SI session tonight at 4:30 in Dunbar 152. So if you want to review reactions and get some more help for the upcoming exam, that's at 4:30. And tomorrow night at 5:30 in Lab 114, I'll do a review session as well. So if you can make it then, I'll be there. What else? If you've seen the exams link on the webpage, I did put a little more information about exam 2 in the link to a list of reactions that you should know. So it looks like everything up through section 6.17. I think that's right. What we covered on Monday's lecture. So, any questions about Friday's exam or any review sessions?
You said 5:30 on Thursday.
Yeah, tomorrow night for my review session will be at 5:30. Yeah, starting at 5:30 and 1:14. Okay. We've been talking and focusing in chapter 6 on reactions of alkenes, and so I sort of summarized this at the end of the last lecture, some of the details, and I think the way to really try to think about making the connections between all the different kinds of reactions. This chart describing sort of the typical reactivity of alkenes and some of the electrophiles and the ways one can do additions has a lot of generalities, but you do need to notice that there are specifics of each one that might be different. So, for example, the general reactivity when we have something that is plus charged, which I've just said generally here as A+, reacts with a double bond because the double bond is electron rich. So the double bond is nucleophilic, it'll react with some electrophile, and that could react depending on specifically what it is that's positively charged that you're adding, will behave in slightly different ways. Okay? It will form some kind of positively charged intermediate, whether that is a carbocation, in which case you need to know that the position that A adds to depends on forming the most stable carbocation, and that's a general phenomenon. Oh, that's interesting. Oh, it's first Wednesday of the month. Or that electrophile, if it's bigger than a proton, such as a halogen, we know, can actually form a slightly different species, a bridging species, which still has some of the characteristics of the carbocation above. Okay, that is, when you add the next group, whatever is minus charge, in this case I've written B minus, that's going to add to the position where the carbocation is. Or in a bridge species, it's also going to add to the more substituted carbon because even though the carbon itself doesn't have a full plus charge on it, there's more plus charge on that middle carbon than there is on an end carbon. So the substitution patterns, the way you think about which direction groups add, is a general phenomenon that we see. And so regardless of this or this intermediate, we see our plus group added on the end and the minus group added on the more substituted carbon. Okay? That's what we refer to as Markovnikov selectivity, because that's the observation Markovnikov made when he first looked at addition of HX or hydration of a double bond. So if you look at the specific reactions that we've covered so far, the acid catalyzed hydration, adding water, H2O, in the form of adding an H plus first, followed by the water, or the equivalent of an OH minus. Okay, the H adds to the least substituted carbon, the OH adds to the more substituted carbon. We can switch that around if we think about an equivalent for an OH plus. But of course, OH plus doesn't exist, right? I mean, if you had OH plus, it would be something that would be super high in energy, and we just can't generate that in the laboratory easily to do a reaction with. So in the case of hydroboration, we use BH3 first, because now we've exchanged, instead of adding an H plus, we have an electrophilic boron atom. And fortunately, we have more chemistry that we can do to convert the boron to the oxygen later. And so the position comes from the idea that the boron is the electrophile in the first step in this process, and then it's converted to OH. So it's the equivalent of thinking about it as an OH plus, if you will, and then H minus. Now, it's not as simple as that, right? Because there are consequences in the reactions of borane that affect the stereochemistry of the product and the position. We just talked about the position, which we refer to as anti-Markovnikov addition. But it's also important to know that both groups are adding on the same side of a double bond, if that matters, right? In some specific examples of alkenes, we see that you will have a difference in the stereochemistry. You could have cis or trans, and this would only give them adding cis or syn. In other cases, like just the alkene I showed above, you wouldn't be able to tell. HX, right, proton and a halide. You can have X2, could be Br2 or Cl2 or I2, in which case you have two halogens adding. And that goes through that bridged intermediate. And the important aspect of that is that because of the structure of, as I scribble all over the slide, because of the structure of that bridged intermediate, it prevents the second group from adding on the same side. So in that case, it's selective for adding anti. So if it matters, if the product is in a ring, then those groups will be on opposite sides of the ring. Okay? So those are the sort of the details you need to remember. You can generalize some of it, but then you have to know a little more specifics about how things are actually happening with each case. And if you think about it in this generalized terms, right, we have something plus adding, A plus, B minus. If we start mixing things up now, and adding X2, which is the first step being an X plus, water then can act as the nucleophile for the second step. So you can actually add different groups. BrOH, ClOH, what we refer to as a halohydrin. The details of regio and stereochemistry are still the same. It goes through that bridged intermediate, it's an anti-addition, and now since we have two different groups, the minus group adds on the more substituted carbon. Okay? So any questions about those series of reactions of alkenes? Okay, well let's continue talking about some other reactions. And I'm going to show you some mechanisms, but I don't think you really need to know a lot of details about it. This, for example, is one way that we could actually change the addition of HBr. Remember in the OH, right, hydration, adding H2O, with acid catalyzed reactions, you generate the most stable carbocation and add the OH. In a Markovnikov addition, we could get around that by adding boron first. This is kind of the same idea. Can we change the mechanism so we could control adding HBr in two different ways? Okay, so in the acid catalyzed condition, what you can do is treat an alkene such as the one shown here with HBr. You get the typical reaction, right? H plus forming a carbocation on the more substitute carbon, and that's where the bromine reacts. What's interesting is if you take this reaction and simply add into it peroxides, could be any number of different kinds of peroxides. In general, a peroxide refers to something with an oxygen-oxygen bond. So I'll just put an R group. Could be any number of things, as long as we have this oxygen-oxygen bond. Peroxides change the mechanism of the reaction. And the reason it changes the mechanism of the reaction is because the oxygen-oxygen bond is relatively weak. Okay? It breaks apart in a homolytic fashion, producing oxygen radicals quite easily. So the nature of the reaction, or the mechanism of the reaction, changes. So if you think about this, we've done something to change the regiochemical outcome of the reaction. But we're still reacting with the same alkenes. We know the behavior of alkenes, right? If we add something to it to form a carbocation, the A plus adds to the end, and the carbocation is more stable. Okay? Well, in this case, it should be clear to you that the reaction isn't starting by adding an H plus, right? Because otherwise, it would be the same as the top. So if you think about it, in order to explain this result, based on what we know, there must be some kind of reactive bromine which is adding first. But we don't have Br2, so we don't have Br plus. This, however, forms radicals. And so we might want to think, well, the mechanism must be changing somehow. And in fact, I'll just share the details of this reaction with you. The peroxides will react. So when you have a peroxide, and this probably is heated, and you add heat to this, okay, you generate two oxygen radicals, so it splits apart. Okay, and what do you know about free radicals and the types of reactions they undergo? Well, they're chain reactions, right? We talked about in the free radical halogenation of alkanes. You initiate radical chemistry, so this is an initiation step. Then you can react some radical with some neutral molecule and get a new radical and a new stable molecule. That's an propagation step. Or two radicals could combine in a termination step. That generalizes radical type chemistry. So what happens here is one of these, if we want to think about an initiation, we can do that with this peroxide breaking apart. If we then want to do a propagation step, it's going to react with HBr. And what do you think it does with HBr? Well, it'll break the H to Br bond. And actually, this will take one electron from that bond with a hydrogen and form a stable alcohol in this case. So that hydrogen came from HBr, and what's left behind? Bromine radical, not a bromide, not a bromine plus. You left behind a bromine free radical. Okay? So now once you've done that, what do you think that bromine free radical can do? It ends up on the organic product somehow. So what do you think it does with the alkene? Well, it's forming a bond, right? And what is the reactive part of that organic molecule? The double bond, the pi bond. So bromine will react just like any electrophile reacts to take both of the electrons of the double bond and leave behind a carbocation. A radical will react with the double bond to take one of the electrons and leave behind a free radical. Okay. Why does it add to the end? Yes, you generate, it's the same concept. Free radical chemistry is a similar concept to carbocations. The more substituted it is, the more stable it is. So it adds selectively on the end to leave the secondary free radical as opposed to a primary free radical. That's the more stable. To continue the propagation, right? To continue the chain reaction, what do you think you have to do with this? Well, it has to produce, again, a bromine radical with HBr, so that radical, I'll draw this as another step here, plus HBr, okay? That's where the hydrogen comes from. That produces the product. Plus Br radical. That Br radical can go back and propagate the chain, react with another alkene, and so on, until various termination steps could take place. So simply by changing the mechanism and the reactive species from cationic species like proton to free radical species, which then causes the formation of Br radicals, you've switched the order of addition. With just the acid HBr, you had the proton first and the Br minus second. If you throw in peroxides, all of a sudden you have this first part happening faster first. You generate Br radical, and that adds first. And it's the hydrogen which adds second. Okay, and that switches the position based on the mechanism. Okay, you see how that's similar to the carbocation chemistry, but we've just changed what the reactive species is we're adding first. Yes?
Will it still follow this mechanism if the hydrogen bromide was diluted?
Was what?
Diluted.
Oh, it would follow the same mechanism if it's HI or HCl. It works pretty well with HBr and HI. It's a little harder with HCl, but I would say it should work. So that bond strength also changes depending on that. The easier it is, and the bigger that halogen, the easier it is to form a radical too. So that also, just like everything else, it gets better as you go down the periodic table.
Yeah, because my worry was that if it's diluted, hydrogen and bromine will be separated in solution and they form ions, which may be more reactive than the
in the presence of peroxides, it will form radicals, and in this case, so you're right. You're thinking too much, because you're right. If you were to do this in water, you'd probably have H plus and Br minus. So when we do these peroxide reactions, we actually do them in other organic solvents. So there are no ions. Absolutely. If you form ions, then it'll add H plus. I didn't put the solvent details on here. That's it.
Peroxides solvent?
Peroxides are not the solvent, they're a reagent added. And theoretically, you would just need a catalytic amount to start the chain process. In practice, we know termination processes tend to hijack the chain processes and stop them. Okay, so that's free radical halogenation. I think I go through the mechanism to try to make all the connections between why things work, because it helps you understand that and remember it when you can't memorize reactions. But what you really need to know is that what I've drawn here, alkene plus HBr, will give Markovnikov addition, but if you have peroxides present, it's going to switch it. Okay? If you remember that much, that would be the kinds of things I would ask. Another functional group I want to talk about is an oxygen-based functional group. So a few of the things we've talked about so far, right? We know we have HOH, water. And if you replace one of those hydrogens with an alkyl group, and we have an OH group left, that's an alcohol functional group. And I mentioned in a few cases that if we have two carbon groups, that's referred to as an ether functional group. So if you have, for example, CH3O, CH3, this is dimethyl ether. Dimethyl ether, okay? When people refer to just the term ether referring to a specific chemical, that's actually diethyl ether. So it's an ethyl group on each side. This is the famous ether that was used in the 19th century as an anesthetic. So you would breathe this ether gas. Not really that safe, but they did it then. Highly flammable too, so people in surgery would, sometimes explode. Doctor coming in with a cigarette, it wouldn't be very good. But in any case, we saw cyclic ethers. So I might have shown you tetrahydrofuran. That's also an ether functional group. So we can have ethers tethered in rings. This was a solvent that we used in combination with BH3 for hydroboration. And there's a special kind of ether which we refer to as an epoxide. And that happens to be a three-membered ring ether which looks like this. Okay? Generally, ethers are relatively unreactive because the carbon-oxygen bonds are pretty strong. There's no reactive OHs to be taken off as an acid, as a proton or anything. And often we just use them as the solvent because they don't participate in a lot of reactions. So tetrahydrofuran is a solvent, or diethyl ether is a solvent. The epoxide, however, is a useful reactive intermediate. And actually, the reactivity of it behaves very much like an alkyl halide in the fact that the carbon-oxygen bond is polarized. But more importantly, because it's a small ring, it's very, very highly strained and reactive. So it's easy to open up. And I think later on in organic chemistry, you learn a lot of different reactions of epoxides. So they're more useful than a lot of ethers for actually using as a molecule to do reactions with. Which brings up the point, how do we make them? And one of the best ways to synthesize these kinds of three-membered ring ethers, epoxides, is through a reaction with double bonds. Okay? And it's an interesting reaction. It's a reaction of what we refer to as a peroxy acid with an alkene. Okay, and again, you don't need to know the details of this mechanism, but I will go through it to help make connections with the chemistry. Because it is a species which is electrophilic. So if we want to think about it, it's kind of like an oxygen which has a partial plus charge. The double bond is a nucleophile. It's electron rich. And so the special thing about this, I guess I should explain. This functional group is a carboxylic acid. RCO2H, a carbon with one double bond oxygen, one oxygen and a hydrogen, so acetic acid. Vinegar has the R group as a CH3 group. And acids, these kinds of functional groups are pretty acidic compared to alcohols because remember that if you have a minus charge on it, you can draw resonance forms with the other double bonded oxygen. So we talked about that when we talked about resonance. Okay. So remember, all the concepts we've talked about from day one in this class, they keep coming back. We can't forget them. In any case, because of that, this group is, because the stability of that minus charge, this group actually is a pretty good electron withdrawing group. And so if you think about now this peroxy acid, we have a peroxide bond, an oxygen-oxygen bond. I just said those bonds are somewhat weak. In this case, it's not doing radical chemistry, but since that's an electron withdrawing group, this part of the molecule, it's almost like having an oxygen which has a significant amount of plus charge. But there's a lot more to it, and it's much more complicated than that. But the nice thing about this reagent, any kind of peroxy acid, it could be peracetic acid, so R could be a CH3. There's one which is referred to often as MCPBA. Actually, it's a little more complicated. Metachloro perbenzoic acid. This is the structure for that. That's used for this kind of reaction. In any case, what it does is when that approaches a double bond, it essentially takes that oxygen and kind of rips it out of this per acid and transfers it, forming both bonds at once, to the carbon-carbon double bond. It's an interesting reaction. The byproduct is just a carboxylic acid, so in this case acetic acid, and the epoxide. So it's a really nice reaction, very good way to make these useful functional groups, epoxides. And again, just one more thing, when you are putting together your list of reactions to know, alkene plus a peroxy acid will give an epoxide. Okay. Reactivity, double bond is electron rich. This oxygen happens to be electron poor, and it transfers over. So there are still even some common general themes we're talking about in terms of reactivities of alkenes. This is another useful reaction. Ozone. Ozone is a reactive species. It's an O3 molecule. And we all know about ozone, right? Where do you hear most about ozone? Ozone is way up in the upper atmosphere, right? And ozone is a very good thing to have way up in the upper atmosphere because it actually filters out a significant amount of ultraviolet light. If we had no ozone, there wouldn't be life on this planet because it is protecting us from a lot of the UV radiation. On the ground, though, it's an environmental pollutant. It's a highly reactive species, and it's produced from smog and burning in cars and things like that. Electrical discharges. I don't know if you've ever smelled, if there's an electrical discharge or a spark, you smell something kind of weird. That might be ozone you're smelling. It's a very reactive molecule. And we can generate it from O2 and electrical discharges. And it can be useful as a reagent. Now let's talk a little bit about the Lewis structure for this. So I haven't drawn any of the charges on here, but obviously there are oxygens here which don't have the right charge, right? There must be formal charges here. In fact, if you add the electrons in here, everything does have an octet, okay? And so where would there be formal charges on this molecule? Right. The middle oxygen has a formal plus charge, and the oxygen on the right has a formal minus charge. Overall, the molecule is neutral, but it's not every atom in it is neutral. All right. We can draw a resonance form for this. Okay, notice we have a minus charge next to a double bond, right? You could draw it this way, and we could draw the same thing like this. Oxygen here, plus and minus. I'm not going to draw all the lone pairs. You should be able to do that by now. So you can draw two resonance forms. The bottom line is that we have a negative charge on the two end oxygens plus charge on the middle oxygen. And because this has a formal plus charge on the middle oxygen, if we can do reactions where that would be, where that plus charge could be removed and satisfied by throwing a pair of electrons on it, then that would be a good thing. So I'm just going to erase this and just mention. So you can also think about this molecule, if you think about pushing these electrons here, that means this might be a positive end or a place that could accept electrons. Now the resonance forms aren't quite right for that, but you can think about that as being a plus minus on either end, what we call a dipolar molecule. Okay? And what's interesting is when this comes in contact with a double bond, it has a very interesting reaction. This is what happens. I'll show you this process. Here's an example. You have a double bond. You have a double bond, okay, this molecule here, reacting with ozone, O3, and then treating it with zinc metal under acidic conditions usually. We get two products out from this molecule. And notice what happened. The double bond, where the double bond was, it's been broken completely apart. Not only does it break the pi bond, but it breaks that sigma bond between the carbons as well. And we produce now two molecules by breaking it apart. And both of them, where the double bond used to be, there's now an oxygen, double bonded oxygen. So it's inserted in between there and put two oxygens in. Okay? So a way to think about that, anytime you see this kind of reaction, ozone will simply break this apart, and where the double bond was, that's where we put a double bond oxygen, 2 molecules. If the molecule is a symmetric alkene, then you'll get 2 molecules, but they'll be identical. In this case, the substitution on either end of the double bond is different, and so we get 1 molecule from the left side, which has a hydrogen here and an ethyl group. That functional group is called an aldehyde. An aldehyde, when you have a R, C double bond OH. And then this molecule would have 2 carbons, 1 on each side of that CO double bond. This is what we refer to as a ketone functional group. Okay, both of them being a CO double bond, which is a carbonyl. And that's a very useful reaction too, because a carbon-carbon double bond can actually be a hidden form of a CO double bond if you want to carry out this reaction. If you're interested in the details of the mechanism, it's shown here. Again, this is not one I would expect you to remember the details of the mechanism of, because it's a little bit complicated. But the reaction occurs because ozone reacts in a fashion like this. Okay? What we call a cycloaddition. We've added 2 groups together, and we have a flow of electrons. Notice you have electrons flowing to one end of the double bond and then flowing from the other end of the double bond to something that's plus. Okay? That reaction produces an intermediate. I lost this part. An intermediate, which looks like that, and then this actually undergoes a rearrangement. It's a pretty complicated rearrangement. I wouldn't worry about it. But in that process, this CC bond is breaking. Okay? And we get this intermediate, which we call an ozonide. You notice some features of this. First of all, if you look at the 2 carbons, which I'll highlight in red here, each of those 2 carbons in this intermediate has 2 bonds to oxygen. So the oxidation state here is the same as the products. The other thing is we have an oxygen-oxygen bond, which is relatively weak. And the second addition here, you might have wondered why we add the zinc to this. And the zinc's job is to actually reduce that OO bond, and then this collapses to form 2 CO double bonds on either end, and actually a molecule of water comes off of that too. So overall, again, the reaction breaks the CC double bond completely and replaces each end of that double bond with a CO double bond. So you can have all kinds of different functional groups, make symmetric compounds, unsymmetric compounds, and sometimes it's useful if you have a molecule which you actually have an unknown structure and you're trying to figure it out, but you know there might be alkenes there. One way in which chemists use to try to examine that or infer what the structure is to carry out this reaction and see if they can identify some of the smaller products after it's undergone this reaction. And then they can figure out where the CO bonds are. They knew what was connected before. Well, let's take a look at something here. Now, one of the main reasons that we go through the effort of learning all these reactions and trying to understand organic chemistry is, as organic chemists, we want to be able to make things. And not everything can you make from one starting material and one reaction and get the product you desire. We often have a limited supply of things that we can get, either from petroleum or nature or whatever. We have starting materials that we can have, but then we want to synthesize more complicated and more complex products. That can't happen in one step. So if we have a goal, let's say let's say you get a job as a chemist in a company, and they say, we need to make this molecule, this 1,5-pentane dialdehyde molecule. Right? That's your job. You've got to figure out how to make that. The company needs that. And they say, well, what we can give you to start with is cyclopentane. Okay? How would you make that? There's no reaction you've learned to go directly in one reaction from cyclopentane to this dialdehyde, right? But we've covered enough chemistry in this class so far. You have been exposed to enough different reactions that you can do that. You can solve that problem. It might take you a while because you're not used to thinking this way, but you should be able to do that. The way we think about this as chemists is to think about a multi-step synthesis, and the best way is to try to think about what reactions we know, starting from the final target and moving backwards until we can get to something that we start with. So I just showed you a reaction, right? I just showed you a reaction of a double bond reacting to form CO double bonds and break it apart. Okay? So, knowing that, if you wanted to make this, what is something you could start with? The reaction I'm talking about, of course, is first reacting with ozone, followed by zinc. Okay, what would you have to start with to get that product from that reaction? Well, it's not two different molecules I've made, but I've made a molecule that has two CO double bonds, right? Two CO double bonds. If this reaction, O3, breaks apart a CC double bond to make a CO double bond on either end, well, where was that double bond at to begin with? Connecting this carbon and this carbon. Okay. So how many carbons is that? 1, 2, 3, 4, 5 carbons, right? And between two carbons, there must have been a double bond. Guess what? We've done ozonolysis on a ring. Okay. If you start with that alkene and you do ozonolysis, what will happen, of course, is you'll break apart the CC bond, then you'll put a double bonded oxygen on either end during that process. That would give you that product. Could you see that? Do you see it now because I showed you, right? How many of you saw that before I put it up? A few of you, okay, good. So that's a start, right? We know we could make the target that your boss wants from cyclopentene, but that's not what we're starting with. Can you think of a way to go from cyclopentane to cyclopentene? No, you can't do that in one step either, right? We haven't learned a reaction like that. Well, that's not true. If you heat it up under high temperature and pressure, I guess you could crack apart alkanes, but it would be very, very difficult here. How else do we know to make alkenes? What methods do you know to make alkenes? This is chapter 5. Hydroboration reacts an alkene to make an alcohol. Yeah. Well, you need to take some functional group and make an alkene. Elimination reaction, exactly. We've learned a couple of eliminations, right? There are two ways to do eliminations. We can do an elimination from, let's see, we could start with an alcohol, right? And we could do elimination with a strong acid like phosphoric or sulfuric acid. Okay, and heat. Right? We can do elimination. Acid catalyzed dehydration. Is there a way you know to go from a cyclopentane to a cyclopentanol? No, not easily, right? There's another way we can do an elimination. What's the other functional group we can use to do elimination? Instead of starting from an OH group, we could start from a chlorine, right? We can do an E2 elimination using a strong base like sodium ethoxide or methoxide. Let's just use methoxide. React with a base, and you can do an elimination under those strong base conditions from a halide. Okay? Now we're getting somewhere because you know a reaction to go from cyclopentane to chlorocyclopentane. What would you need to do that? A substitution, but specifically, since we're substituting a alkane hydrogen for a halogen, what conditions do we need? What do we need to react with? You're thinking, yeah. Yes. Acid catalyzed halogenation. And if you do an acid catalyzed halogenation, what kind of functional group do you react that with? That's an alcohol, yes. You need to protonate an alcohol, make a carbocation, and add the chlorine. So that we don't have an alcohol to start with. We just have alkane. You're right, we could do that. We could take this alcohol and we could react it with HCl and do a substitution. Right? These are all the reactions that you have coming up on the exam. You could do that, but we can't get there. Still can't get to that alcohol. Yes?
To produce the chloroalkane, we can react the compound above with the chlorine in the presence of UV light.
Chlorine in the presence of?
UV light.
UV light, yes. You could take chlorine gas, Cl2, and you could react that with a photon of UV light, or you could use heat. I think your book mainly uses heat for that, actually, right? Heat or light activation of chlorine, and you can do this reaction, which goes by what mechanism? Free radical halogenation. Okay, so I want to start getting you thinking about what kinds of specific reactions you know. What is the functional group transformation that they undergo? And if you can start to be thinking in this way, then a problem like this might not be so difficult to see. I mean, right? It probably looks a lot like a black box to you now because you haven't been used to thinking in this way. But the more of a repertoire of reactions and functional group transformations you learn, the easier it is for you to see that. And to be honest, it takes a long time to get to the place where that becomes more automatic. But notice what we have going on here. Halogenation, substitution. Someone mentioned substitution. Yeah, you have to substitute a hydrogen for a chlorine, and we only know this way to do that from an alkane. It was brought up, substitution of an OH group for a chlorine. Yeah, that's a reaction we can do under acid catalyzed conditions. What's the mechanism for that reaction? How does that reaction proceed? OH, you have alcohol, react with HCl. Okay. You protonate the alcohol. What do you form? You form the OH. I'm running out of room, sorry. You form an OH plus. What happens from that intermediate? First you form the carbocation, and then chloride, will react. SN1, yes, very good. Just to let you know, for the exam, what I expect you to know, first of all, if I give you a starting material and reagents, can you figure out what the product is, right? What is the product of that reaction? If I ask you to give a product, I would expect you to know the details of that reaction, right? Will it know what is the regioselectivity? Markovnikov, anti-Markovnikov. Is there stereochemistry that's important? Is it a syn addition or anti-addition? Those things you should know when you draw that product and indicate very clearly. Mechanistic details, all these reactions where we have carbocation intermediates. The main types of reaction mechanisms, you should know what initiation, propagation, termination steps are in radical chemistry. And also things like, the mechanisms that we've talked about for both alcohols, halides, as well as reactions of alkenes, right? We have elimination under carbocation conditions, elimination not under carbocation conditions, but strong base conditions, E2. And we have substitutions, whether it's carbocation, SN1, or SN2. Okay, and the details of that you really should have a good sense of. Okay, since we're talking about some of these carbocation rings, I want to take the last couple of minutes and see what's next on here. Yeah, and just talk about alkenes and their significance and importance, because this reaction is quite important. The reaction of alkene with itself. Most of the time under radical conditions or under acid catalyzed conditions. So this is an example of like the first start of that. If you take an alkene such as 2-methylpropene, react it with concentrated sulfuric acid, what comes out are a couple of alkene products. But notice, we've added 2 of these alkene molecules together. This is referred to as a dimer because we've taken the one alkene, often referred to as a monomer. We've carried out a reaction to form a combination of them and dimerized it. So how do you think that's happened? How do you think that's happened? General idea about reactivity of alkenes, right? We have an alkene and an acid. Alkene is electron rich. Acid will protonate it, right? And will form one carbocation selectively. The hydrogen added here, plus charges here. Now we have a dimer. What might happen with that plus charged molecule? Well, if we have water, water will add. If we have another alkene, which has electron density, guess what? Another alkene can add. Right? Let's see if I can draw this. That's the hydrogen we added first. I should have put that in a different color. This is the bond that we just formed. You generate a new carbocation. Guess what? Those products come from that carbocation removing a proton, eliminating a proton. If it eliminates from one of these ends, you'll get this product, and if it eliminates from here, you'll get the more substituted double bond. Well, that's an example of a process which could continue and go on and on and on, right? What happens if this product now, we have this carbocation here. What happens if it reacts with another double bond? And another double bond, and another double bond. And so what you can do is you can get a whole bunch of reactions that occur in a row. Guess what that forms? A polymer. By the way, the same thing can be done with radical intermediates, and even more commonly with radical intermediates than carbocation intermediates. So polymers, polyethylene, a bunch of double bonds of ethene that have been polymerized or connected together through this type of cationic or radical process. Polystyrene, some of you might have a styrofoam cup with you, with your coffee in it. Same thing, monomer doing this chain reactions to give polymer. Okay. Again, don't forget, SI session tonight, review session tomorrow night, exam Friday. And check out that list of reactions on the exam setting.